Building on the idea that homeostasis is balance, I'd like to once again conceptualize homeostasis as a teeter-totter. Of course, the teeter-totter, the position of the teeter-totter, is the thing that can change. Therefore, this is the variable, and we're trying to maintain a neutral position. We define this neutral position where we want the teeter-totter to be as our set point. And of course, the teeter-totter can move. It could be displaced either up or down, and this range of motion is what we call the normal range. Now I'd like to highlight the integral components of a homeostatic feedback loop. What happens when an outside or external force, known as a stimulus, causes the teeter-totter to deviate away from set point. In this example, let's place a child on one end of the teeter-totter. Without being too distracted by my amazing artistic ability to draw that child, I think we can all recognize what's going to happen. As the child sits on the teeter-totter is displaced away from its set point. Now, in order to restore balance, we need to be able to detect the change in the variable. This requires a receptor. We'll draw our receptor here in a way that allows us to easily see as the teeter-totter moves up and down, the receptor can detect this. Now, once a change is detected, we need a decision maker, something capable of interpreting the change and understanding how to restore balance. We'll call this the control center. There are just a few things left. First of all, we have to set up communication between the receptor and the control center. This communication can happen in lots of different ways. We call this the afferent signal. And lastly, while the control center can prescribe a remedy, we do need something to actually fix the problem. We call this the effector. And in this case, we'll draw as a boot that removes the child from the teeter-totter. And to complete our loop, we have to set up the communication now between the control center and the effector, and we call this the efferent pathway. Now, I would like to highlight the fact that in this system, two things can change the variable, both the stimulus and the effector. The difference being that the effector is under control of the control center, while the stimulus, as defined earlier, is an outside force, an external force that can change the variable. Now, with our feedback loop intact, let's see if we can apply this to a normal, everyday biological system. Let's look at blood pressure. We can define the set point of our teeter-totter as a typical blood pressure reading with systolic and diastolic measurements of, say, 120/80, measured in millimeters of mercury. And in reality, there are lots of different stimuli that could change our set point. Some that we're easily familiar with would be, for example, exercise, where the increased movement of skeletal muscle would cause increased circulation of blood and increase our blood pressure. In contrast to this, we might see a loss of blood. This could be from a bleed, from blood donation, or simply being dehydrated, and that would lead to a decrease in blood pressure. Of course, we need a receptor to detect this. The receptor that detects blood pressure is called a baroreceptor. The baroreceptor is simply a stretch receptor in your carotid artery, and it is regulated by stretch. For example, at a normal blood pressure of 120/80, we would expect to see normal stretch in a cross-section of the carotid artery, so maybe it looks like this. However, if our blood pressure goes up, we would expect this to increase in stretch. Likewise, if our blood pressure goes down, we would expect to see the stretch decrease. And it's the change in size of this baroreceptor that sends the afferent signal to the control center. In this case, the control center is going to be the brain, and the afferent signal is carried along a neuron. Now, one of the first responses that we would see to compensate for the change in blood pressure will be a change in our heart rate. So in this system, the heart will be the effector. The communication between the brain and the heart, our efferent pathway, can either be direct via a neuron, or it can be through signals in the blood, endocrine signaling. And this completes our homeostatic feedback loop for regulating blood pressure. So let's try to graph this response. If we were to graph time on our x-axis and blood pressure on our y-axis, we can see in the middle our set point, and we can define our normal range. Let's first look at the example of a blood donation. Of course, they stick a needle in my arm, they start pulling blood out of my body. That will lead to a decrease in blood pressure. So my blood pressure begins to fall. Of course, part of the long-term response is making sure I get enough fluids, I'm drinking, I'm eating. But the short-term response is, as the baroreceptors sense that decrease in blood pressure, they communicate with the brain, and the brain sends an efferent signal to the heart, telling the heart to increase its heart rate. And as the heart starts to beat faster and stronger, my blood pressure starts to rise. And we go back to set point. This part of the graph where we are returning back to set point is called negative feedback. But let's consider another scenario. Perhaps a severe arterial bleed. Again, I'm losing blood, And so my blood pressure falls. Of course, very similar to our previous example, we would expect the heart rate to increase in order to compensate for this loss of blood pressure. But here we see an issue. As my heart rate increases to try and increase the blood pressure, this simply has the effect of causing me to bleed out faster. And so rather than going back to set point, the effect of the increased heart rate has on my body is to pull me further away from set point. And now we see an example of positive feedback. There are two key aspects of the definition of positive feedback. First, I'm going away from set point. And second, I've gone beyond my normal range. And where negative feedback will always restore set point and bring me back into balance, positive feedback brings me away. Of course, that means that the ultimate effect of positive feedback, unless rectified, is death. Certainly there are instances of normally occurring positive feedback in the body. Childbirth is one, blood clotting is another. But most examples of positive feedback occur, like the scenario that we just described, when negative feedback loops become broken.